Hello guys, welcome to this video. So today I'm going to be giving you some preliminaries into how to interpret, or actually how to interpret the Latin mnemonics for the first figure, second figure, third figure syllogisms. And I'm going to show you how to prove them using two methods of proof actually. And then yeah, and then that's basically going to be it. We're just going to cover some preliminaries first, so that just means I'll get into like the basics of the syllogism, and then we'll get into the methods of proof. Alright, so let's start with what I gotta cover. Okay, so a syllogism, well, a classical syllogism at least, a classical syllogism, right? Let me kind of, let me see. Okay, a classical syllogism is one where it has two premises and one conclusion, in which Aristotle did say what is supposed the what is supposed, which is the premises, and what results is of necessity. So meaning given two premises, the conclusion necessarily follows or is produced from the premises as the effect, basically like that. Let me make this, or stretch it. Okay, so that's just the basics of a syllogism. If I were to give you an example of a famous syllogism, I would just do the all men are mortal, Socrates is a man, therefore Socrates is mortal, where the conclusion necessarily follows from the premises, in which the premises necessitate the conclusion. Now, in a syllogism, we use certain kinds of sentences. We call them categorical sentences, right? And categorical sentences are simply sentences with a subject and predicate. So, we use categorical sentences for classical syllogisms, where categorical syllogisms are sentences with subject plus a predicate. So if I were to give you the example, this tree is green, this tree is the subject, while green is the predicate. Now for Aristotle, whenever you have two pairs of contradictory statements, like let's say Socrates is sitting down or Socrates is not sitting down, one of them, that forms a contradiction, but one of them has to be true and the other one false, right? But that will be covered in my Aristotle's logic video, which is coming up later. But yeah, so these are really just the basics of what you gotta know for a syllogism. Now, for categorical sentences, however, we classify them, or there is a mood for them. We the mood of a categorical sentence is its quantity plus its quality. So quantity relates to, it's either universal or particular, and in quality is whether it is positive, affirmative, or negative. And I'm using affirmative and positive interchangeably here, so this is how you would classify. So for example, if I said every man is mortal, this would that every indicates a universal quantity, and it's affirming, so it would be called a universal affirmative, or universal positive, if you want to say that. So that's just one quick example, and that leads us into the square of opposition here. So the square of opposition is a really fun tool for logic. It's been used for a long time actually. And so let's quickly go over the Aristotelian square of logic. So in the Aristotelian square of logic here, we have four moods of a so in the square, oh, let me type it out. In the square of opposition, we have four moods for categorical sentences. So we have A, E, I, O. So first of all, let me just see if I can expand it. So A represents the universal affirmative, which you see every S is P, and an E represents the universal negative, where no S is P, and an I represents the particular affirmative because it's just saying some S is P. Oh, sorry, I forgot to write it out. Universal negative for E, I is the particular affirmative, and an O is the particular negative. Now, the relationships in the square of opposition they do differ from each other. So contraries, that is A and E, where both cannot both be true at the same time, but both can be false. Subalterns is simply where the superaltern, which is A, actually, let's not make it complicated. It's where one implies the other, but the other doesn't imply the one back. So this would be relationship between A and I, or E and O. So for example, if I were to give you an example of this, if I said all men are mortal, which is a universal claim, I can logically say that some men are mortal, right? Which is true, right? If all men are mortal, then it does imply some men are mortal. But if I just went from some men are mortal, I cannot just say all men are mortal, because that's a huge leap. You see, first I'm reasoning from the universal to the particular, but I can't reason from the particular to the universal without, obviously, some induction. But this is classical syllogism. So these are subalterns, where one implies the other, but the other one doesn't imply the one back. So A implies I, but I doesn't imply A back. Now, subcontraries, which is the relationship between I and O, they can be both true, but cannot be both false at the same time. And so that is really just a general relationship. A contradicts O, I contradicts E, right? So that is the general relationship between the moods of a categorical sentences. So just note that the mood of categorical sentences is its quantity plus its quality, right? And so that's basically all you have to know for the square of opposition, and that's basically it for the square of opposition. Next, let's cover the mood of a syllogism and its figure and all of its terms. So we'll do that now. Before we get into that, actually no, never mind. We don't have to do that. But yeah, so a mood of a syllogism is the order of the mood of its categorical sentences. So for example, if I say all men are mortal, and Socrates is a man, and I can conclude that therefore Socrates is mortal. Socrates is mortal. This I can classify. So remember, the moods of categorical sentences include A, E, I, O. So 4 letters, right? Now we can classify each categorical sentences based on what they are. So here you see that all men are mortal, so we see that's a universal affirmative. And then if you go to 2, you see Socrates is a man. Now, this is where it might get a little complicated, because this is an example of a Barbara syllogism and AA mood syllogism. AA mood syllogism above. And you might wonder why Socrates is a man is actually a universal affirmative in this case, because universal affirmatives can actually express singular statements, which are just categorical sentences about a single thing. So Socrates is a man is logically equivalent to all persons identical with Socrates are men, or all that Socrates is a man. So a universal affirmative can actually express a singular statement, right, about a single thing. And so that is why the last two categorical sentences are logically universal affirmatives. And so we have an AAA mood here, and then we need to figure out the what figure it belongs in. Now, because the figure is defined, figures of syllogisms is defined simply as the order of the placement of the middle term in respect to the premises. And the premises differ as well. So, for example, we have a major premise and a minor premise. But it's putting that aside right now. The first figure. Oh, I don't know what just happened. Oh, well, I gotta close my thing. Okay. The first figure syllogism is where the middle term. Oh, let me actually define middle term. The middle term is the term that appears in both premises, either as subject or predicate. So the first figure syllogism is where it's going to be first subject, then predicate. Second figure syllogism is where it's going to be both predicate, and then third figure is both subject. While fourth figure, which is also known as the indirect first figure, is where it's going to be switched, so it's first predicate, then subject. So if I were to give an example of both, let's say you just have the simple, it would look like this: MP, and then you see SM, and then conclusion is thus SP. So you see here where the middle term M is first subject and then predicate here, and so that's how you would read it for in this case. And then both predicate, so it would be PM, or one PM. Oh, sorry, not yeah. PM, SM, and therefore SP. So that would be a example of a second figure. And then third figure is simple. It's M, MP, MS, right? Both subject, and then SP. Fourth figure, it's just literally the same as first, but flipped. So 1 PM, MS, and therefore SP. So that would be the figures of a syllogism, right? Make sure you take notes on this. This is really good to know. Now, to expand my radar here on this thing. Oh, it's not really expandable. So I'm just going to delete all this. Okay, so I deleted that. Now, there is what we call a major premise and a minor premise, and a major term and a minor term. A major term is the predicate of the conclusion, while the minor term is the subject of the conclusion, right? Where the major premise is the premise containing the major term, while the minor premise, as you might have guessed, is the premise containing the minor term. the minor term. So in the case of of the Socrates syllogism, we see that man is the middle term, mortal is the major term, and Socrates is the minor term. And Socrates is a man is the minor premise, while all men are mortal is the major premise. And this is a first figure syllogism, and you could go up to the chart, but it's a Barbara syllogism. If you go up to the chart, it's a valid, perfect Barbara syllogism. And so in the first figure. Now, you need to know that Aristotle held what is it called? He held the first figure syllogisms to be perfect syllogisms. Perfect syllogisms in the sense that, they don't need more terms. They don't need anything else to prove them. They're just perfect. So they're kind of like self-evident. While Aristotle introduced us to what's known as imperfect syllogisms, where they do rely on the first figure for their, for their proofs. So, without further ado, we shall distinguish. So all you have to know is that the first figure syllogisms, Aristotle considers self-evident. These are perfect self-evident syllogisms, not needing any proof. Now, Aristotle divides our division of proof into two categories. Aristotle's proofs are divided into a twofold division. And how do I say it? There's a proof through the impossible and a proof through direct deduction. Oh no, that was what I was trying to say. I'm sorry. So Aristotle says a deduction is perfect if it needs no other term no other term outside of it in order to show the necessity of the conclusion, right? So that would be Barbara. Example Barbara, because that's the most perfect syllogism. And a imperfect syllogism is where if it needs one or more in addition that are necessary because of the terms that were already supposed but were not assumed through the premises. So that's just to quickly go over what a perfect syllogism and a imperfect syllogism really is. But okay, so for Aristotle, there is a two division of proof, right? So in proofs for imperfect deductions or syllogisms, Aristotle reduces each one to the perfect syllogisms or forms, and thus are completed or perfected. This can happen through a reductio. This can happen through a proof of the impossible, or in other words, a reductio ad absurdum. Okay, and so a reductio ad absurdum is where you negate the conclusion. So negating the conclusion, the desired conclusion, and then reasoning. Actually, let me make this thing more closed in here. So it's negating the desired conclusion, and then reasoning to a contradiction with an earlier premise to show that it contradicts one of the earlier assumptions. Okay, so this is known as a proof through the impossible. Now, a direct deduction is really just a process. Leading from the premises to the conclusion, and where there's either what we call a conversion. There's either a conversion of a previous premise or an inference from two previous premises relying on a first figure deduction. So conversion is inferring from a proposition another which has the subject and predicate changed or interchanged. So really, Aristotle says there's only three conversions that are sound. So he gives us three, right? So first, A, E, and I, and no O. So Aristotle says the universal affirmative can logically be converted, while the universal negative can also be, logically converted. And I, the particular affirmative, can also be logically converted. So, for example, A, which is the universal affirmative, can logically convert to the particular affirmative, while E converts to the universal negative, and then I converts to the I again. So every S is P is logically converts to some P is S, and no S is P logically converts to no P is S, and then I, if some S is P, then it logically follows that some P is S. And so these are the three sound conversions. Now, in the Stanford Encyclopedia of Philosophy, you might see a bunch of notation like this. So, this is just to give you an insight into what it looks like in the Stanford. Now, this is read as no B is A, and then it converts to no A is B. Where you see that it so be careful, because in the Stanford's notation, you first read the predicate and then you read the subject. So no B is A. EAB is no B is A, right? And here, some B is A converts logically to some A is B. And here AAB, where every B is A, converts logically to some A is B. And so this is what the notation will look like in the Stanford table. And so these are just really the three conversions you must know in order to, to even prove, if that makes sense. Now going back to really the basics of a syllogisms, you might also encounter what we call extremes. The extremes are just the major and minor term, and then there's something called the copula, which is just the is when. So I just wanted to clarify those terms if you've heard of those terms, but you wanted just to, ask like what it is. And so okay, so I think we should get started onto the Latin mnemonics and start proving a bunch of our syllogisms here. Okay, so where is the Stanford table? Let me just delete all this because it's taking up way too much space right here. Okay, so here is the Stanford table. Now do not be, how do I say, do not be shocked if it looks like a lot, because I know it looks like a lot for sure. But yeah, so in the first figure, you see that these are perfect syllogisms, as Aristotle said. They're self-evident, while the other figures are imperfect, because to make it plainly evident how, their conclusions follow from the premises, we require like conversions, or, just an inference from an earlier premise or whatever. And then we got a reductio. We could also prove it via reductio ad absurdum. Okay, so as I've said, there is three sound conversions. Let's actually go over the basic notation of the table here if you want to understand it. So, I do not unfortunately have the what is it called, the flip T that the Stanford table uses. But for example, if I take Barbara here, I can read it as, because all B is A and all C is B, therefore all C is A. So that is how you read this one. So if you, that's that's just how you want to read it. And then the proof of it, because it is perfect, it doesn't need proof. It's where other syllogisms are proved via, Barber. Okay, so the rules for interpreting the mnemonic go like this. Because the mnemonics were used by Latins to memorize the proof of syllogisms, to memorize the mood of syllogisms, and really just how to prove it, right? So the rules for the mnemonic is really just that: one, the vowels are what indicates the syllogism's mood. So if I were to give you an example, I keep using Barbara. Barbara. Where Barbara. Where you see there's three vowels, Barbara indicates an AAA mood. So vowels indicate the mood of a syllogisms, that is that its categorical sentences are universal positives in this case for Barbara, right? The first letters of imperfect syllogisms indicate what perfect first figure syllogism is needed to complete their proof. So for example, chemistries in the second figure is going to be completed by celerant, right? Because celerant is a first figure syllogism. Now, this is where we get into the proofs, really. So an M means swap. So M means swap the ordering of the premises. C, following a vowel indicates that you need a reductio ad absurdum, or reductio, or proof through impossible for that syllogism. But you only don't worry, because this only applies to Boccardo and Barocco. Okay, so, and that's basically what you have to know for C. And now a P, the letter P after an A means converting that that universal affirmative to a particular affirmative. So really it's just an A conversion on that categorical sentence. Okay, now a P, but like a P on the end, for example, like I think it's Darapti. No, not Darapti, but I'll cover it when we get there. But so an S actually after an E, an S after E or I in the syllogism just means use a E or I conversion on that categorical sentence. And so the other letters are practically just there. They really don't do anything. But that's basically all you have to know for interpreting the Latin mnemonics right here and how to prove them. So let's get started in our first proof, shall we? And I'll go step by step with you, my friend. So let's keep this rule on the side right now because, it will help us, and maybe you'll see the whole reasoning process. But okay. Okay, let's see. Let's try chemistries first, since I mentioned it. I hope you guys can see that. Can I move this thing so it's closer so you guys can see it? Okay, I think I'm gonna have to make this bad boy a little bit bigger. There you go. There, that's more how do you say it? Visual. Okay, so chemistries. So the chemistries here is AAB, EAC, and then therefore EBC, which is really says that every or all B is A, all B is A, and no C is A, and we want to prove the conclusion that no C is B. Now I structure my proofs differently from Stanford a little bit, but it's still valid. So here this is a proof, so we're trying to direct deduction of chemistries. So first I want us to indicate what syllogism is needed to complete chemistries. So we know that because of C as the first letter, we need celerant. And because we know there's an M here, M after M in the middle of A and E means swapping the order of the premises, and S, so S indicates a conversion of E in that second premise, and then S in the last after the last E indicates a conversion of the conclusion. So really, let's get into the proof now. Enough of me yapping. So to prove that no C is B, we know that we have to swap the order of the premises. So that means no C is A comes here, but because we had to convert it, it becomes no A is C, right? Because M indicates swapping the order of the premises. So no A is C, right? And then we converted no C as A via the S after the E, because remember, a universal negative can convert to another universal negative. And then 4, we restate premise 1, all B is A, and then you can logically conclude that no B is C, and this is 3 for celerant, right? And then we can logically convert it again, because remember, the S after the last E indicates the conversion of the conclusion. So no C is B, conversion of 5. And there you go. That's how you really just generally prove this, right? So let's retrace. So first, I indicate that chemistries is going to be proved via a celerant syllogism via the letter C. And then I know M means the swap of the ordering of the premises, so I swap premise 1 and premise 2. And so premise 1 will come after premise 2, where you see premise 3 is no A is C, and then I restated premise 1, which is premise 4 now, and then I conclude no B is C, which is valid because look, it's a E syllogisms, and celerant is an EAE syllogism, and look, its middle term is subject then predicate, and that logically follows that it is celerant, right? It's a first figure celerant syllogism, and then I just converted the conclusion from celerant to no C is B, and therefore I get the original conclusion that I was trying to prove. If you can see on the Stanford table, they wrote it in notation as well. Now, for people that are confused why the celerant syllogism here isn't matching up to the Stanford table, mine is like this. So mine goes, no A is C, all B is A, therefore no B is C. This is literally the same as theirs. It's just switched. So what that means is every B is A. This is theirs, by the way. Oh, that just got smaller. And then sorry, their celerant syllogism is no B is A, no B is A, every C is B, therefore no C is A. Notice how this is literally the exact same thing. Just look at my terms, they're just switched, right? This is exactly the same thing right here. And so that is how we proved chemistries via direct deduction. Now, let's say we wanted to prove chemistries via a proof through the impossible. Now, the reason why Stanford does not include a proof through the impossible for chemistries is because it's simply not needed. Rather that it can be directly deduced. But for the sake of this video, let's just do that. So let's do a indirect proof, or proof through the impossible. the impossible for chemistries. So here, it's not going to obey the same rules, so meaning that it's not going to be reduced via, I mean, it is reduced to Celerant, but it's not going to be, we're not going to be using Celerant for its indirect proof. So let's start over again. So let's go, so chemistries is every B is A, or all B is A, no C is A, and we want to prove the conclusion that no C is B, right? We want to prove the conclusion that no C is B, and then to simply prove that, we assume the negation of E, which is, we can assume that every C is, every C is B. Let's assume that every C is B, right? Every C is B, and then we can restate the conclusion that, I mean, not the conclusion, I'm so sorry. But we can restate that all B is A, and then we can conclude, thus, all C is A. But it was assumed that no C is A. And then, so this is 3-4 Barbara, and I'll show you why in a minute. So, but it was assumed that no C is A. So 5 contradicts 2. Okay, now notice the problem here. Let's see. When we say this is 3-4 Barbara, notice here that my middle term is lacking, meaning that my middle term is first subject, is first predicate then subject. So it's not a first figure. So what we got to do here is we switch the order of the premises. So let me just take that right there. There you go. And now we have properly a proof through the impossible for chemistries, and this logically follows, right? So here we see that no C is B contradicts every C is B, and all B is A, via, just we restated premise 1, and then this is Barbara because look, it's an A syllogism. The middle term is subject and then predicate. Thus, this is how we would prove chemistries through the impossible. So all I did was assume the negation. You could also add another conclusion and just say, thus, by contradiction, no C is B. You could add that if you want. I just don't do it, but and that's basically how you would prove chemistries via an indirect proof, or reductio ad absurdum. But also, really here, you can also reduce chemistries again. So let's just do chemistries again. So chemistries is all B is A, right? And then no C is A. And then we want to prove the conclusion that no C is B. Now, we did in fact assume a negation of that conclusion earlier, but really that conclusion was just a contrary to E. So because this is an E statement, we have to find what contradicts, right? So these are contradictories, or so I contradicts E. So no C is B, and then we assume that some C is B. Some C is B. And then we can bring down premise 1. So we can bring down premise 1, where all B is A. So all B is A. And then we can logically conclude that some C is A. But we can reason and say that, but it was assumed that no C is A. So where I did 2 proofs, I did one where the negation was a contrary, and then I did one where there's a contradictory. So here, in the square of opposition, you see that I contradicts E, right? And then, but yeah, let's retrace our steps. So 5 is 3-4 Dari, right? If you see on the table, Dari is every B is A, some C is B, therefore some C is A. But if you realize the problem again, we have to switch the ordering here in order to make it work right here. And so there you go. There you go. That's all you have to do. So you can really do a lot of indirect proofs here. This is just one example of it. Um, but let's go through another direct proof. So let's see what we want to do. I'd say let's do this psalmist. This psalmist, right? So first we realize the D indicates it's going to be completed via dari, right? Dari syllogism. And the S after the I indicates the particular conversions. So both premise 1 and conclusion, because look, there's an S after the first I, and then there's an S after the last I, and then M M indicates swapping of the order of the premises. So let's really just get started on proving this. So first, the sum is some C is A, every C is B, or all C is B, all C is B, and we want to prove the conclusion that where is it? To prove that some B is A. So here we know that we have to swap the order of the premises. So premise 2 is coming first. All C is B, and then we convert premise 1. Therefore, some A is C. That a conversion of premise 1. Premise 1. And then we can logically conclude that some A is B. And then we can logically conclude it again to some B is A. Right? So I know that's a lot of steps, but let me quickly explain. So first, because we realize that it's going to be proved daddy, and then we realize there's an S after the first I, indicating that we have to convert the first premise, and then we see an M indicating that we have to swap the order of the premises. And so, and then the S after the last I, which is the conclusion, means we have to convert the conclusion. So here you can see that their proof does it too. So for example, it goes from some C is A and then all C is B, and then we switch the ordering of the premises and we go it switches from here. It goes every C is B, and then we have some A is C, and then we can conclude that some A is B, and then we convert it back to some B is A. And so that is a direct deduction of the psalmist. This direct deduction. And in the syllogism we use to prove is daddy, obviously, because you know the letter D indicates it. And so let's say we wanted to prove the psalmist via reductio ad absurdum, right? Proof through the impossible. Since we already proved it, direct deduction through the impossible. So the psalmist is some C is A, every C is B, and we want to prove the conclusion that some B is A. So first we need to look at the square of opposition and see what contradicts the I statement. So let's do E. So let's assume that no B is A. No B is A, right? There's just no B that is A. Okay. Alright, if no B is A, but every but every C is B, so we can restate premise 2, every C is B, and then we can conclude that no C is A via 3-4 Celerant, right? But it was assumed some C is A. So here obviously here it is obviously Celerant, because you have an EAE syllogism where the middle term is first subject and then predicate, so that logically follows from Celerant, because Celerant is right here. No B is A, every C is B, and therefore we can conclude that no C is A, but it was assumed that some C is A, thus by contradiction some B is A necessarily. And that's how you would prove the psalmist via proof through the impossible. So you can prove syllogisms direct deduction and proof through the impossible, except for Barocco and Boccardo, which they have to be proven through reductio ad absurdum. Alright, let's go through some few more examples. Let's do Festino. So, Festino direct deduction. So, first we can observe that the letter F, because Festino is a second figure, we can indicate that, not because it's a second figure, but that because of the first letter F, indicates it's proved by Ferrio. S after the E indicates conversion. So let's prove Festino. So Festino is no B is A, some C is A, some C is A, and we want to prove the conclusion that some C is not B. So if we want to prove that, realize that the S after the E indicates the conversion. There is no M, that means no swapping. So we can really restate just the first premise. No B is A, and then premise 4 we convert. I'm sorry, we convert premise 1, but we just restate it, but then convert it. So no A is B, conversion of premise 1, and then we can restate that some C is A, and then we can conclude via Ferrio that therefore some C is not B. And this follows logically because this is Ferrio. Ferrio is an EIO syllogism, so EIO, and the middle term is subject and then predicate. Thus, it logically follows. And so that's how you prove Festino. So 3, 4, Ferrio. Okay, and let's say we wanted to prove Festino via direct deduction. I mean, not direct deduction, indirect proof, or proof through the impossible, because I'm really just going through two. Now, the only reason why I'm doing these both proofs is because one, of course, Festino is obviously going to be proven via Ferrio, but when I'm doing proof through impossible, I just want to show you the methodology and how we do it. So Festino is no B is, we can just literally pop this down. Alright, so to prove that some C is not B, which is an O categorical mood, we can assume the universal mood, or the mood of A. So assume that every C is B, right? Just assume that every C is B. But we know that no B is A, and then we can conclude that no C is A. But it was assumed. Some C is A. So here from 5 we from 5 we concluded 3, 4 celerant. Notice that this is celerant, but we have to switch the order of the premises right here. So this really just goes down here. This goes up here. So notice here that this is celerant. So no B is A. We restated premise 1. And then we assume the negation of the conclusion, which is some C is not B. We assume that every C is B because A contradicts, O. And so we can reason, therefore, that no C is A, but it was assumed that some C is A. So thus, by contradiction, we can indirectly prove that some C is not B. And that's how you basically do the proof through the impossible for Festino. Let's do one more example proof for direct deductions. Let's do Darapti. Where is Darapti? Alright, Darapti. So first we can know that the letter D indicates it's proven by Dari. And then we know the P after the second A vowel indicates a particular conversion of that A. So let's prove it. So Darapti is simply every C is A, every C is B, and we want to prove the conclusion that therefore some B is A. We know that P after, so we just restate premise 1, every C is A, and then we convert premise 2, then we convert it to some B is C. So that's conversion of 2. and then we can logically conclude therefore that some B is A. And that would be a 3-4 deity syllogism, which logically follows, which is an AII syllogism. And that's how you prove dadapti. And obviously you can see in their proof goes like this. For Stanford, it goes like this: AAC, ABC, and then you just prove that. And then you go AAC, ICB, and then because I don't have the T, I'm just gonna, yeah, just do something like that. And then I'm pretty sure I can go, can I? No, I cannot. And then it goes like this. Okay, so their proof looks something like this. And this exactly matches mine, so every C is A, every C is B. To prove that some B is A, we restate premise 1, so every C is A, and then we convert premise 2 to some B is C, and then we can logically conclude that some B is A. So this is what I mean when their proof is different from mine. It's just I add the extra to prove, or I restate some premises. You don't have to. But actually, I think you do. But I would recommend just doing it, because you know. Okay, so that is how you directly, how do I say it? Directly deduce dadapti, right? Okay, so let's see. Let's say we wanted to reduce dadapti via indirect proof. So, or we want to prove dadapti via reductio ad absurdum, reductio proof for dadapti. So we know that some B is A is an I categorical sentence, and then we can assume the negation or the contradiction that no S is B. Assume the contradiction of the thing, or assume the negation of the desired conclusion. So assume that no S is B. Oh, I'm sorry, I just looked at the thing. Assume that no B is A. Assume that no B is A, but every what is it called? Every C is B, and then we can logically conclude therefore that no C is A. But it was assumed that it was assumed that every C is A. So here again we from 5 we conclude 3 for Celerant. This is Celerant's conclusion, by the way, that no C is A. So Celerant goes from no B is A, every C is B, and then therefore no C is A. So that was Celerant, but it was assumed that every C is A. Thus, by contradiction, we have proven. Thus, by contradiction, some B is A. So we really just proved it indirectly. If you want to see how I did it again, right? So for an indirect or an reductio ad absurdum, reductio proof goes like this. Assume negation of desired conclusion. Use that with an earlier premise to derive a conclusion that contradicts an earlier assumption or premise to indirectly prove the conclusion via contradiction. So that's how you do that. So here, that's how I did it for dadapti, right? If I say every C is A, every C is B, and I want to prove that some B is A, I just assume E, because E contradicts I, that some B is A, but then we say no B is A, and then we restate premise 2 that every C is B, and then we conclude via a first figure syllogism, EAE, that no C is A, which is Celerant, by the way. But it was assumed that every C is A. Thus, by contradiction, some B is A necessarily. And so that is how you would prove that. Okay, so let's get into there's an interesting thing in the table that I wanted to point out. Here, look at Dari and Ferio can be reduced via impossibility. So I just want to show you something. So let's go Dari. So Dari can be proven. So Dari in reductio goes like this. So because Dari is every B is, or all B is A, some C is B, and we want to prove the conclusion that some C is A, and we know that is an I, so we just assume that no C is A. Assume that no C is A, right? Because E contradicts I. No C is A, and then we can restate premise 1 that all B is A, and then we can conclude therefore that no C is B, thus no C is B. And that is 3 for chemistries, by the way. So this is chemistries, but it was assumed that some C is B, thus by contradiction, some C is A. So that is a Dottie reductio via chemistries. So in the table, they don't give you the whole notation proof for Dottie, but this is how you would prove Dottie via reductio from chemistries. And let's do Ferrio, because Ferrio is proven from Cesare via Reductio Ad Absurdum. So Ferrio is no B is A, some C is B, and we want to prove the conclusion that some C is not A, right? Okay, to prove that some C is not A, we assume the negation, and we say that because that is an O particular, the conclusion that we're trying to prove is O, a O mood, we assume that every C is A, and then we restate premise 1 that no B is A, and then we can logically conclude, therefore, no C is B. Therefore, no C is B. So, there you go, and then we assume that, no C is B. Now, you can also switch the ordering of the premises, like for premise 4, you can also switch it, because Cesare is an EAE syllogism, we just switch it. So right here, this is switch, by the way. Just erase that right there. So now this can be. So we restate premise 1, no B is A, and then every C is A. So we have to switch it, remember? And then therefore we conclude that therefore no C is B, but it was assumed that some C is B. Thus by contradiction, some C is not A, right? Because the whole proof why the proof follows is because if we assume the negation of the conclusion, but we show the negation of the conclusion leads to an impossibility, it indirectly proves our desired conclusion. So, there you go, and that's how you prove Ferrio and Dottie via Reductio Ad Absurdum. Now, the Boccardo and the Barocco proofs are, oh, I'm sorry, excuse me, I just burped. They're interesting in the sense that, you have to prove them via Reductio Ad Absurdum, but let's do one more proof. I just want to do one more proof. Let's prove Philopton for indirect deduction. I mean, not indirect, direct deduction. So Philopton is no C is A. Oh, Philopton, so we see that P, so F, we have to write our steps. Remember, F indicates Ferrio to complete it. P after the A indicates particular conversion, and I think that's it. Okay, so let's start proving Philopton. So Philopton is no C is A, all C is B, and we want to prove the conclusion therefore that some B is not A. Now we know that Ferrio completes it, and we know that we have to convert the second premise. So we restate premise 1 that there no C is A, and then premise 2 logically converts to some B is C, and then we could logically conclude therefore that some B is not A, and that logically follows because that's 3 for Ferrio. So that's how you would prove Philopton here, if you can see, by the way, my friends. And that's basically the Philopton proof. And I think you can also do a reductio for Philopton, though it does take a little bit of time to find. So let's do a Philopton reductio ad absurdum. Philopton reductio. So the Philopton reductio we just, copy and paste this right here back because I don't want to rewrite it again. So because Philopton's conclusion is some B is not A, which is an O, we have to assume, we can assume that every B is A. Assume that every B is A, and we know that all C is B, and then we can conclude that therefore every C is A, or all C is A. And this would be a Barbara syllogism. This is Barbara, by the way, Barbara, because Barbara goes every B is A, every C is B, and therefore all C is A. But it was assumed that no C is A. Thus by contradiction, some B is not A. And that's how you would do a direct deduction for Philopton, and then a reductio for Philopton. Alright, so the interesting part about this is that the only syllogisms in this table that really ever need a reductio is going to be Boccardo and Barocco. And so let's see Barocco. I'll show you right now. So Barocco here doesn't tell us much. It just tells us that, that it needs to be proven, right? Because it has a C in it. Boccardo and Barocco, that vowel, right? That C following the vowel indicates a reductio proof. So let's just prove Barocco, right? Barocco. So Barocco goes like this. Proof for Barocco. Reductio. So it goes like this. So Barocco starts off as all B is A, some C is not A, some C is not A, and we want to prove the conclusion that therefore some C is not B. Well, because this is a O, or a O moved for that categorical sentence or conclusion right there, we assume the negation. We assume that every C is B. If we assume that every B is C is B, then we can restate premise 1, and that is every or all B is A. All B is A, and therefore we can conclude therefore every C is A. But it was assumed some C is not A. Therefore, by contradiction, some C is not B. And so that's how you would do Barocco, right? So here you see we assume the negation. Oh, and then make sure this is proper. So we switch this with the assumption here to make it fit for the because the middle. Remember, if we're going to use Barbara to reduce this, so this is Barbara, by the way. If we're going to use Barbara, make sure the middle term aligns in the correct place for the right figure. So here, RB is A. We really just restated premise 1. We assume that every C is B, which is the negation of the conclusion that we're trying to prove for Barocco. And then we reason that every C is A. But it was assumed that some C is not A via the earlier premise. So we showed that there's a contradiction. And then we can indirectly conclude that some C is not B. Alright, so the last proof I will do will be Boccardo, which is also going to be reduced via Barbara. So Boccardo simply goes like this. Some C is not A. But every C is B, and we want to prove the conclusion that some B is not A. So obviously this is an O, right? This is a O mood for this categorical sentence. So we assume the negation. So assume that every B is A. Every B is A. And we know that every C is B because we just restate repetition. This is what we call repetition, by the way. Repetition of 2. And then we can conclude, thus, thus all C is A. But it was assumed that that some C is not A, right? So here, obviously this is Barbara, because if you go back to the top, we assume that every B is A, we restate premise 2, which is just repetition. Every C is B. Then we can conclude that all C is A. But it was assumed that some C is not A. Thus, by contradiction, some B is not A. Ricardo proved via reductio. And so that is just how you would get a outline of the general proofs. Make sure you use these rules to prove syllogisms. These are very useful. And that is how you interpret the Latin mnemonics and improve them. I hope I gave you an insight into the basics today. But basically that's it. Thanks for watching.